In Chapter 16, we begin our discussion of kinetics, or rates of reactions. And so an important thing to think about is when we talk about reaction rate, we're talking about a change in a quantity as a function of a change in time. So what we have here is a plot for how we think about rate. And we're showing again the change in the concentration of a species as a function of time. And so that's indicated by this red line here. So we predict that this is for a reactant in a concentration because we can see that the concentration is decreasing as time goes on here. So there's three kinds of rates that we want to think about. We want to think about average rate, instantaneous rate, and then a special kind of instantaneous rate that we call initial rate. And so that's what's represented by 5 different kind of regions in this plot here. So let's take the first one here, which is an average rate. And to kind of give you an analogy, an average rate might be, for example, in my car, I have a diagnostic on my car that will tell me that my average speed is like 47 miles per hour. And so that's looking at a whole bunch of data over an extended period of time and saying that I'm averaging about 47 miles per hour. Now, at any given point, I might not be going 47 miles per hour, but taking the average of that over several time periods allows for that average. And so we have 3 averages that we're looking at here. And so the first average looks at over the entire course of the reaction, so from time equals 0 to time equals 60 seconds. So what we can see here is we're looking at this entire time from this first time point all the way to this next time point. So it's shown by this line A here. Right, so that's really representing what we're seeing here. And so what we'd really like to think about is what the change in quantity over that time period is. So we can really look at the change in the concentration of ozone. So that's, again, this change in Y over this change in X. And so if you put those quantities in, you'll actually end up getting a rate that's 3.5 times 10 to the minus 7th molar per second. Okay, so that's our average rate. We can have average rates that span different time spans. For example, this is an average rate that just looks at the first 10 seconds of the reaction. And what we can see here is that this rate is faster. So as the reaction begins and there's lots of reactant, this reaction is a lot faster as when we're starting to run out of reactant, and it becomes much slower at the last 10 seconds of the reaction, which is shown by C here, looking at the C domain. But in any of these, again, change in a quantity over a change in time is really, in this case, the change in Y over change in X, which is the slope of a line that we draw. So if we're looking at, for example, A and B and C here, we can see that the blue lines that we're drawing that represent the change in Y over change in X, the slope of these lines is different. Okay, it's the smallest here for our last time point when the reaction is slowest. It's the fastest for our early 10 seconds, our first 10 seconds. And then the average, which includes all of the time periods between 0 and 60 seconds, is kind of an intermediate between those. Okay, so average rate is pretty easy to think about in terms of, a change in a certain quantity as a function of time. So again, as we decrease concentration over a certain time period, what's that change in Y over change in X? And because we're picking 2 discrete time points, we can actually calculate or estimate from our graph here what the change in X is and then what the change in Y is. Change in Y over change in X will give us our rate. Okay, so the other points here are instantaneous and initial rates. And again, once we learn what instantaneous rate is, the initial rate is really the instantaneous rate at time equals 0 seconds. But let's talk about what the instantaneous rate is. As a little bit of an example, an instantaneous rate is going to be, thinking about my car analogy, that's going to be the speedometer on my car. At any instant, I can look at that and that will tell me my speed at that instant. I can push on the accelerator and my speed will change. I can slow down and coast and my speed will go down. And again, that diagnostic on my car, that average rate might change as I spend more time going faster or more time going slower. but my speedometer is going to be my instantaneous rate. Okay, so how do you figure out an instantaneous rate if you're looking at a specific time period? You're not looking at a range in time where you can get a change in x. Well, what this requires is a little bit of data interpretation. So for example, at the instantaneous rate at 35 seconds, what we need to do is we actually need to make a line that we're going to infer a change in y and a change in x over. So we need to draw a tangent to our curve at time equals 35 seconds. And this is where this kind of method can introduce a little bit of human error, because depending on how you draw this blue line is going to change what your change in y and your change in your x variable are. So determining instantaneous rates, because you're not choosing actual data points on your line, you're drawing a tangent to this curve and then choosing and making your own data points that you're using to figure out your change in x and your change in y. There is a little bit of error. Imagine having this kind of curved a little bit more that way. It'll make our y a little bit bigger and our x a little bit smaller. Take it the other way. It'll make the change in y a little bit smaller, the change in x a little bit bigger. So there is some inherent error built in with figuring out instantaneous rates. And again, the initial rate really just represents drawing a tangent at time equals 0. And as we can see, just looking at the slope of this blue line here for E, that's going to be our fastest. So, and that makes sense. As soon as this reaction starts, when we have the maximum concentration of O3, of ozone, our reaction is going to be the fastest. So again, I didn't go through each individual calculation for how you figure this out. But remember, rate is just equal to the change in our concentration of ozone here over a change in time. And again, because this is disappearing, we're going to have a minus here. We're going to always have final minus initial, so we're going to have the change in ozone concentration final minus the change in ozone concentration that you started out with over time final minus time initial. This time parameter will always be positive. Don't forget our negative here. In our case, because the final concentration is always going to be less than our initial concentration is always going to be this value here. So one of our final concentrations will always be something that will be smaller than what we start with. That means this value is going to be negative. But again, that's why it's important when we write a rate expression for a reactant that's disappearing, we put a minus there, because that allows our rate in units of molar per second, again, which really is moles per liter second. This is always going to be positive. Rate is always positive. So final minus initial, and again, if it's a reactant that's disappearing, we start out with a larger amount than we end up with. So that difference will be negative, and that's resolved to a positive value by having that negative there. So all of these values here were obtained by taking these differences and plugging them into here. For this one, it's 60 seconds minus 0 seconds was the initial. And again, using the concentration that we end up with at ozone at 60 seconds versus the initial concentration. Those are all worked out in detail within your book, so you can see those actual calculations as well as in the lecture notes